Now we will try to understand the definition of dimension. So number of elements in basis set of vector space V is called as dimension of a vector space V. Now just now we have seen the basis set of r raised to n contains how many vectors? N vectors. So therefore dimension of r raised to n will be n. The basis set of Pn of x contains n plus 1 vectors. So therefore dimension of Pn of x will be n plus 1, and the basis set of M of m cross n over r contains mn vectors. So therefore dimension of this will be mn. Now what can you say about dimension of singleton 0? Remember, it is a bold 0, right? So the dimension of singleton 0 is always what? 0. Okay, just keep this in mind. This is very important. And our basis set in this case is what? The empty set. Okay, empty set is the basis of this singleton 0. Now next, now what is given to us here is one vector space is given and its subspace is given. Now we already know that subspace means what? It is a vector space itself. So therefore we can find dimension of subspace as well. But in order to find dimension of a subspace, we should know the definition of basis, because we need to find basis of W in order to get dimension. As we know, the definition of dimension is what? Number of elements in the basis set. So simply we will try to recall the definition of basis of vector space V. So a subset B of V is said to be a basis if first B is linearly independent, and the second condition is what? Linear span of B is equal to V. But here we have to find basis of W. So in order to find basis of W, there will be some changes in the definition. What will be that? So we have to find a set B such that B is a subset of W. Next, B is linearly independent, and the second thing is linear span of B is equal to W, since we have to find basis of W. So what we will do is, first of all we will find a set B such that linear span of B is equal to W, and then we will check whether this B set is linearly independent or not. If it is linearly independent, we will directly say that B is basis of W. So I will do for first example. I will solve this example, and these two example I leave for homework. So chalo, let us go for the first example. That is, W is equal to collection of XYZ such that this X plus Y plus Z is equal to 0. Note what is our vector space in this case, that is R3. So now this W further can be written as set of all XYZ such that X is equal to minus Y minus Z, which is further equal to, it is a collection of, so simply put the value of X here, that is minus Y minus Z, Y as it is, over here Z as it is, such that now there are two variables, so such that YZ belongs to R, which can be further written as, now you take this Y out, so inside the bracket, now see, in the first coordinate Y is present. What is the coefficient of Y? Minus 1. So I will write minus 1 here, comma. Now in the second coordinate Y is present, so its coefficient is 1. But in the third coordinate Y is not present, so therefore its coefficient is 0. Plus, now I will take Z out, Now in first coordinate, coefficient of z is -1, so I will have -1 here. Z is absent, so it is 0. Now z is present, but its coefficient is 1, such that z belongs to what? R. So if you carefully see this set, just recall the definition of linear span. So if you are having set of the type set of all alpha 1 v1 plus alpha 2 v2 and so on alpha n vn, such that this alpha i's belongs to R, then we were calling this set as linear span of B, where what is our B? Where B is a set containing this n vectors. Now over here also, see this y is a real number and z is a real number, so this are nothing but what? Our v1 and v2, right? So you can treat this y as alpha 1 and you can treat this z as alpha 2. See, there is nothing special about this notation. Just try to understand, this alpha 1, alpha 2 and alpha n are real numbers. So over here also we are having real numbers. So actually this is nothing but linear span of B, where B is nothing but what? If linear span is defined in this way, then B is containing n vectors. Note, there is a summation involving how many terms? N terms. So here also there is a sum actually, but it is involving 2 terms only. So in this set we will have 2 vectors, namely -1, 1, 0 and -1, 0 and 1. Remember, what is the left hand side? That is W, right? So what we have done here is, we have found out a set B such that linear span of B is equal to what? W. Now it remains to check whether this B is linearly independent or not. If this B is linearly independent, then we can say that this B is basis of W and we can tell the dimension of W. So let us check the linear independence. So what I will say, let alpha 1, now you are already familiar with this. Therefore you can say that from 1 and 2 both the conditions are satisfied. So from 1 and 2 you can say that B is basis. B is a basis of what? W. So therefore what is dimension of W? Now since basis set contains 2 vectors, so therefore dimension of W is 2. So that is what we wanted to do here. Now so 6th and 7th are for homework. Now we'll go for 8th example. So finding dimension of what? Note, we have to find dimension of set of solutions of these 2 systems. So over here I have taken simple systems for understanding purpose. So I will solve this second system. So this first system is for homework, and believe me, it is very easy example, the first one. So in order to find the dimension of solution set of this system, first of all we will find the solution set of this system and then we will go to find its dimension. Okay, so our system is x plus y plus z is equal to 0 and y plus 3z is equal to 0. So in order to solve this system, I will directly write down the augmented matrix. So our augmented matrix is 1 1 1. X term is absent, right, in the second equation, so its coefficient is 0 1 3. Over here 0 0. Now see, so therefore over here rank of A is equal to rank of what? This augmented matrix, and both are what? 2, but which is less than 3. That is nothing but our number of unknowns. Now you know, whenever our rank is equal of matrix A and augmented matrix, and it is less than number of unknowns, then our system has infinitely many solutions. Therefore system star has infinite solutions. Now let us solve the system. So we already have this system to be in echelon form itself. So we already have this matrix to be echelon. So we already have this matrix in echelon form only. So directly I will write the equivalent system. If this is not in echelon form, you have to convert it in echelon form, right, in order to find the ranks. So equivalent system is, and it is the same system, that is x plus y plus z is equal to 0 and y plus 3z is equal to 0. So over here number of parameters will be how many? That is, it comes from here, right? 3 minus 2, that is equal to 1. So I will put parameter for z. So put z is equal to t. Therefore from second equation, by using 2, your y plus 3t is equal to 0. Therefore y is equal to what? Minus 3t. Remember, this t is a real number. Next, now in order to get 3, I will call it as some 4. So in order to get the value of x, I will say use 3 and 4 in 1. So therefore x minus 3t plus t is equal to 0. Therefore x minus 2t is equal to 0. Therefore x is equal to what? 2t. Yes. So therefore what is our solution set? So our solution set is nothing but what? It's a collection of x is 2t, y is minus 3t, and z is nothing but what? T, such that t belongs to, right? So I will call this solution set as some w. Now what we have to do is, we have to find the dimension of this w. Okay, so we have w is equal to somewhat like this, which can be written as, if you take t out, so 2 minus 3 1, such that t belongs to R, so which is equal to. Now again try to recall the definition of a linear span. Now if in this summation there are n vectors, then this is linear span of B, and where B is containing these vectors, right? Now in this case there is only one term, isn't it? So therefore this is equal to linear span of B, where what is our B? Our B is containing only one vector, and which is that 2 minus 3 1. So we have found out the set B such that linear span of B is equal to W. So this part is done. Now it remains to check that whether this B is linearly independent or not. If this B is linearly independent, then we will directly say that this B is basis of W, and we'll get the dimension of solution set of the given system. Now you already know, since B contains single non-zero vector, right? Therefore B is linearly independent. So from this 1 and 2 you can easily say that, therefore from 1 and 2 this B is basis of W, and therefore what is dimension of W? Now basis set of W contains 1 vectors, so therefore dimension of W is 1. So that's all about now. Then we will go for few important notes. So first of all, the second note. So whenever we are having W1 and W2 as subspaces of vector space V, then we are having a formula. In fact, we can prove it also. Dimension of W1 plus W2 is equal to what? Dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So this is intersection of subspaces. So this first note is actually important. So over here the vector space V is given, which is finite dimensional, and W is given to be a subspace of V. So W is subset of V naturally. Now if we are having basis of W, so what we can do is, in that basis of W we can add some vectors and we can get a basis of V from it. I will repeat again what I am saying. If we are having a basis of W, that is a subspace, so we can add some vectors in that set. Okay, over here I am calling that vectors as Vk plus 1, Vk plus 2 up to Vn. So we can add some vectors in the basis of W to transform that basis to what? Basis of the vector space V. So in other words, we can say that in finite dimensional vector spaces, basis of subspace can be extended to the basis of vector space. So this is about first note. Thank you.